This is the handout that is in your Google Drive folder. And it should look very familiar because you received this in honors chemistry, most of you, and in AP chemistry, some of you. These are the three kinds of naturally occurring radiation: alpha, beta, and gamma. And what I would like you to see in particular is, first of all, their relative charges, because an alpha particle has 2 protons. It's got a charge of +2. My beta particle is an electron, charge of -1. Another thing that we should notice is the relative masses. Being pure energy, of course, there's no mass for a photon. And you can see how much less massive an electron is compared to 4 protons and 4 neutrons. Ionizing ability is very important. This is the ability to make ions, as the name would suggest. And when you make ions in a cell by knocking electrons out of their orbitals, off of their energy levels, these ions then can do an awful lot of damage in a cell because they mess up the chemistry of the cell. They can create free radicals, is a phrase that sometimes is used in the literature. And so alpha particles would have the highest ionizing radiation because they're so big. When an alpha particle enters a cell, it's not too difficult for that alpha particle to smash into a protein or a piece of DNA or a subcellular structure and do damage. A beta particle would be much less ionizing because of the fact it's just a very, very small electron. And gamma radiation would be the least ionizing of all because it doesn't even have mass. An analogy would be if you had a shop, and in that shop you sold lots and lots of very delicate crystals and glasses and porcelain objects and china. An alpha particle would be like if some bull or horse walked in the front door and you had a bull in the china shop. It would do an awful lot of damage. A beta particle would be kind of like if you had a big bumblebee that got in the front door. It probably is not going to do a whole lot of damage unless it actually did fly into something very, very small and delicate. And a gamma ray would be like light coming in the window of the door or the picture window of the shop. You wouldn't expect it to do much damage at all. Now, fortunately, the penetrating ability is just the opposite. Alpha particles have the highest ionizing energy, but it's got the lowest penetrating ability because it's not traveling very fast. It's a little too big to travel very fast. Your skin, for example, can block most alpha radiation. Beta radiation, which has medium ionizing radiation in the sense of in between alpha and gamma, and it only has moderate penetrating ability. And then gamma rays, which don't ionize much at all, can very easily get inside cells by a factor of 1,000 over alpha radiation. And of course, how would radiation get into your body in the first place? Ingestion, inhalation, which would be very damaging because it would get into your lungs, or injection through a cut or through a needle, something like that. Now you might remember this from chemistry as well. Comparing uranium-238 to uranium-235. Notice that most of the uranium on the planet is uranium-238. A small percentage is uranium-235. Now you might wonder, well, what difference does that make? The answer is, in order to sustain a chain reaction, which we'll talk about in chapter 30, you need 4 to 5% uranium-235 in a nuclear reactor, or the nuclear reactor won't work and you will not be able to generate any significant amount of electrical energy. So in a nuclear reactor, somehow we got to go from 0.7% and enhance it up to 4 to 5% uranium-235. And the way you do that is by figuring out a way to get rid of some of your uranium-238. For example, we have a certain percentage of girls in our classroom. We could increase the percentage by getting some of the guys to leave. Here we could use gaseous centrifugation or gaseous diffusion to get rid of the more massive uranium-238, thus increasing the percentage of uranium-235 left behind in our sample. This would be called reactor-grade uranium. Now, in order to get bomb-grade uranium, you've got to operate those centrifuges or that diffusion process much longer. It's much more extensive and expensive because a nuclear weapon has got to be over 90% uranium-235. And it's interesting to note that Iran, for example, is at 20% and counting uranium-235. And deep underground, they have lots and lots of centrifuges at work. A few years back, about Christmas time, a computer virus somehow wrecked all the controls for their centrifuges. And we know a little bit about how that happened in the collaboration probably between Israel and the United States. But now they're back at it again, and this is published information. They're up to 20%. And why do you need that? You certainly don't need that for a nuclear reactor, as if you needed nuclear reactors to generate electrical energy with all of your oil. The other thing you should note here is a reminder in chemistry of the difference between an atomic number and a mass number, which are whole numbers, and then your atomic mass, which is your weighted average, which is the weighted average of the isotopes of each of the forms of that particular element. If we had time, we could go through the calculus of how we derive this equation at the very bottom that you're using in your homework and that you saw in the text. And here's some examples of nuclear reactions. The first three are decay, natural decay, the spontaneous emission of alpha particles or beta particles or gamma rays, and in the process becoming either a different element altogether or becoming a more stable element from the metastable state. You can also have, besides emitting a beta particle like this, you can emit its antiparticle, a positron. K capture refers to the opposite of beta emission, where you absorb a beta particle instead of lose it. And it's called K because way back when, this electron in the outer shell was called the K electron. Now, by the way, if you're asked, and you will be, to write nuclear equations for the decay process, remember that the decay process produces alpha, beta, and gamma. So the alpha, beta, and gamma goes on the right side of the arrow where you would put the products. Every year there are students that don't do that right. They put the alpha, beta, gamma on the left side for some reason. Now here's an example of the difference between uranium-238 and uranium-235. When uranium-238 gets hit by a neutron, it just gets absorbed. But when uranium-235, and plutonium-239 for that matter, get hit with a neutron, it splits into two daughter products, and it releases more neutrons, which actually then could turn right back around again and strike more 235 nuclei if they're in the area, and we would call that a chain reaction. More about that in chapter 30. and more about fusion in Chapter 30, where we can take small nuclei, fuse them together to get bigger nuclei. In both cases, you get huge amounts of energy, but to be truthful or to be fair, all of these produce a little bit of energy, but this is how we would produce energy for commercial purposes. And if we wanted to create or synthesize, make elements that do not naturally exist, like curium, we would take an already existing big element, like plutonium, and smash smaller particles into it. And hopefully they stick and we make elements that don't exist. Finally, you could calculate your estimated annual radiation dose. How much radiation are you exposed to every year? Well, a big part of it is where you live, and that depends upon altitude. The higher up you go, the more you're exposed to. That also depends upon, for example, what kind of house you live in. And you'll notice that your proximity to a power plant, especially coal, is important because when coal burns, a lot of radioactive isotopes go into the air. You get a little bit from food and water, a little bit from how you live. Now, TVs today are no longer this technology, cathode ray tubes, so you can just pretty much get rid of that 1 millirem. Smoking is a voluntary way of introducing the radioactive products. There'll be trace amounts of it in the burning of smoke into your lungs, which is one of the worst ways you can introduce it into your body. Your medical tests would be significant. And you'll notice that if you are near a nuclear power plant, 1/100th of a millirem, there is so little radiation, practically none, that comes from generating electricity in a nuclear reactor. And one last math problem as an example. If we were to take plutonium-239, which does not exist naturally on the planet, we have to make it in nuclear reactors, and bombard it with a neutron, we get 2 daughter products, and we get 3 neutrons, which we could use to strike 3 239 plutonium nuclei, which would give us 9 neutrons, and very rapidly you would get a lot of energy being produced. How much energy is produced? Well, the way that we calculate that is we take our reactants. Here are my reactants. They're what we start with. This is different than chemistry. In chemistry, we always did products minus reactants. But in physics here, to find our energy, we have to find our nuclear mass defect. So we have to take the masses that we start with, the reactants. There's the plutonium. There's the neutron. Then we subtract my products. There's tellurium, molybdenum, and of course those would come from charts. Here's my 3 neutrons. And when we subtract, we get our nuclear mass defect. The missing mass. The mass that we started with is more than the mass we ended with. Why? Because some of that mass is converted into energy. And you could either convert it straight into mega electron volts by multiplying by 931.5 MeVs per nucleon, or you can take your nuclear mass defect, convert it into kilograms. The kilograms would be your mass times the speed of light squared, which gives you your joules. And this is something that's done for the sake of comparison to other nuclei. You would divide by the total number of nuclei, 240. which is the 239 from the plutonium and the 1 from the neutron. And on your test, you're going to have to do this calculation where you're going to be finding your energy per nucleon. So make sure you add up all the nucleons, protons and neutrons, on the left side of the arrow. And then this is the number that you would use to compare the energy from one nuclei that is being split to other possible ones. That is called your binding energy, and you might recall that in lesson 1, we looked at a graph of different binding energies.